Yes, welcome friends once again for module 4 frequency domain analysis of control engineering for 7th semester for session 1. So these are the learning objectives. The first one is relationship between time and frequency domain, and in which polar plot, Nyquist polar plot, Nyquist stability criteria and relative stability, and some of the learning outcomes, that is frequency response analysis using polar plot, frequency response analysis using Nyquist plot, and relative stability. Here in case of frequency domain analysis, the term frequency domain analysis here refers to the steady state response of a control system subjected to a sinusoidal input. So here the equation for sinusoidal input is given here, that is A sin omega t. So here A is a fixed amplitude, but omega is the frequency which can be varied over the certain range, and t is the time period. So here whatever the input you can give to the control system, it will generate some output. So here the input will be sinusoidal. So once again the output will be in the form of sinusoidal only, with some phase shift, that is phase angle. So here the output from the system under such circumstances will also be sinusoidal of the same frequency. Frequency remains same, there is no change in the frequency as compared to input and output, but only the difference in amplitude, that is A. So and a phase angle, a shift in the phase angle, that you can see in the the equation. The input and output waveforms are sketched below here. So here we are having the input, that is A sin omega t, that is starting from the the origin with some amplitude A. The equation already given, A sin omega t, that is applied to the control system, and the output will be of the same sinusoidal, that is B sin omega t plus phi. So here the amplitude is taken as B as compared to earlier it is taken as A, in order to differentiate the difference in amplitude. So once again here the amplitude may be same or different, that is depending upon the what kind of system you are applying here, but the waveform, that is sinusoidal only. So here for input, that is amplitude is A, for output the amplitude is B, and here the input sin omega t, but here in case of output, that is sin omega t plus phi, because there is a shift in the angle, that is called the phase angle or phase shift. You just see in the output waveform, it is not starting from the origin, it is some distance from the origin, that is taken as phi, that is phase angle or phase shift. That is the input waveform, that is the output waveform. So once again the frequency remains same, that is with respect to the x-axis. So here the ratio of amplitudes with respect to output to the input, the ratio of amplitudes, the amplitude of waveform for the output sinusoidal wave to the amplitude of waveform of input sinusoidal wave, that is the ratio of B by A, is called magnitude ratio, and is denoted by m omega. That is denoted by m omega. That is also called as phase angle, or phase shift, which is given by once again phi omega. So here the magnitude ratio and phase angle are different. So magnitude ratio is m omega, and here the phase angle or phase shift, that is denoted by phi omega in degrees. The variation of this m omega versus omega and variation of phi omega, that is phase shift or phase angle with respect to omega, are graphically studied and represented by various plots. So here the variation of magnitude ratio with respect to omega, that is angular velocity, and once again the phase shift, that is phase angle with respect to omega, that is once again studied graphically here using some 3 different plots. That one is polar plot, Nyquist plot and Bode plot. So first we can concentrate on the polar plot, how to draw the polar plot, and what are the procedure steps required here to draw the polar plot. So here the polar plot, the introduction to the polar plot. This plot is called polar plot since the polar coordinates are used to locate the point on the S plane. So this plot is called polar plot because we are using the polar coordinates, that is r and theta. But in case of Cartesian coordinates, which parameters we are varying or considering, that is x, y and z. So basically in two dimension we are going for x and y. So here in case of polar plot we are going to considering the polar coordinate, nothing but the radius and theta. The same point can be represented using Cartesian coordinates as well as through the polar coordinate. The only difference is in case of Cartesian coordinates we are taking the coordinate along x-axis and y-axis, but in case of polar coordinate we are representing a point in the the plot or maybe S plane by taking the radius and theta. Okay. So one more thing, the advantages of polar plot is that a single plot is able to reveal the variation of both, that is magnitude ratio versus omega, that is frequency, and phase angle or phase shift versus once again omega. So thus, which is also called as 2-in-1 graph. In only one we are having variation of two parameters can be studied here, and here the relation between the Cartesian and polar coordinates is expressed here, which is mathematically given by, so the r equals to x square plus y square to the power 1 by 2, or which is also called as r equal to square root of x square plus y square, where x equal to r cos theta and y equal to r sin theta. So I told in polar coordinates we are taking the radius and theta, r and theta. So note here the first polar plots, m omega is treated as r here, nothing but radius, magnitude ratio is taken as r here, and the phase angle or phase shift which is treated as theta. So hence r and theta are the two active parameters in case of polar plot, nothing but magnitude ratio and phase angle or phase shift. So here we are going to mark the negative value of the theta in the clockwise direction. So we are always, in case of Cartesian coordinate 360 degrees, we will mark the angle from 0 to 360, that is anti-clockwise, that is first quadrant, second quadrant, third quadrant, fourth quadrant. So 90 for each quadrant, hence it is 360 degree. But here in case of polar plot we are marking the angle, that is in the clockwise direction, those angles are negative in values, nothing but minus 90, minus 180, minus 270 and minus 360. If you take minus 90 in case of polar plot, that is also taken as 270 in case of the Cartesian. No, it is anti-clockwise, but here in the clockwise we are going to mark minus 90, minus 180 and so on. And here the procedure to draw the polar plot that you can see here. The very first thing, the procedure for drawing the polar plot of system whose transfer function is given, transfer function that may be the open loop transfer function or closed loop transfer function. So that you should know, then only you can draw the polar plot for that particular transfer function. So what is the first step? Note down the given transfer function carefully, for which it is required to prepare the polar plot. Further identify its type number and order number. It is very much required. So type number and order number will tell the moment of polar plot. So that will tell, in future we can discuss what is type number and order number when we solve some examples. And second step, adjust the term if necessary to 1 plus st form. If it is already in the 1 plus st form, no need to adjust. If it is not there, we adjust into 1 plus st form. That will be easy to draw the polar plot according to this procedure. So for example, if it is 1 plus 2s, need not be adjusted. It is 1 plus 2s need not be adjusted, but 2 plus s need to be adjusted, as we take the 2 common. So it is 1 plus s by 2. 1 plus s by 2. So 1 plus something should be there, st form, or 2 into 1 plus 0.5 s. 1 by 2 is taken as 0.5 s, and the s square terms to be adjusted as s into s in the denominator of that transfer function. So very second step is adjust to 1 plus st form if necessary. Otherwise, if it is already given, no need to adjust. And s square term, that is adjusted as s into s. That is step number 2. Coming to the step number 3, replace each s by j omega. Replace s by j omega, where j is s square root of minus 1 or minus 1 to the power 1 by 2. That is imaginary variable or parameter. So replace s term by j omega in the third step. And the fourth step is, once again, that is obtain the equation for m omega and phi omega, that is magnitude ratio and phase angle or phase shift, using the following relationship, that is m omega equal to real square of numerator plus imaginary square of numerator to the power 1 by 2, or it is also called as square root of real square of numerator plus imaginary square of numerator whole divided by real square of denominator plus imaginary square of denominator to the power 1 by 2. Okay, that is for magnitude ratio. And similarly for the phase angle or phase shift, that is phi omega equal to tan inverse of imaginary by real of numerator minus tan inverse of imaginary by real of denominator. So here how to get the phase angle or phase shift, that is in terms with respect to the variable of polar plot with respect to theta, that is phi omega, that is equal to tan inverse of imaginary by real of numerator minus tan inverse of imaginary by real of denominator. Okay, this is the step number 4. So here, where real is the real part of integer and imaginary is the imaginary part of integer of transfer function, and n is indicates numerator and d indicates denominator. That is step 4. Coming to the step 5, putting the limiting values of omega as 0 and infinity, because we are varying the value of the omega between 0 and infinity separately, and obtain the corresponding m omega and phi omega, based upon which the sketch is to be drawn that will have the approximate shape of the graph. It is convenient to obtain a third point in between, if wherever possible, to understand the shape of the graph correctly. So here only two limiting values we are substituting in step 5, that is 0 and infinity. So only we will get two endpoints of the graph. So you want another third point in between that will tell the nature of the graph. It is convenient to obtain a third point in between wherever if possible to understand the shape of the graph, nothing but the polar plot correctly, and obtain the value of m omega, that is magnitude ratio, and phase angle or phase shift wherever the plot crosses the real or imaginary axis. So once again here, sometime the polar plot may cross the imaginary axis. So the point of intersection with the imaginary axis, you need to find out the magnitude ratio as well as the phase angle or phase shift. Next, step 6, if it is required to draw the polar plot, Then calculate m omega and phi omega for few selected values of omega in the vicinity of crossover and tabulate. And taking a suitable scale, locate the points using polar coordinate system and draw the smooth curve passing through all points to obtain the required polar plot. So this is the first session. So once again we can have some brief. So here the learning objectives that we have discussed, learning outcomes we have discussed, and what is frequency domain analysis that we can discuss. So here the waveform that is for input A sin omega t and for output B sin omega t. So here A and B are constant, nothing but the amplitudes. A is the amplitude of input waveform and B is the amplitude of output waveform. And omega t frequency with time domain. So there in case of omega t plus phi, there is a shift in the phase angle, that is phi in case of output waveform. So here for both the input as well as output waveform, the frequency remains same, that is same frequency, but only difference is difference in the amplitude and a shift in the phase angle. So that's shown here with sketch here. Once again, that can be studied using so many plots: polar plot, Nyquist plot and Bode plot. So very first polar plot we have discussed the general procedure how to draw the polar plot. Here that we discussed, we are taking the polar coordinate as the variables in case of polar plot to represent magnitude ratio and phase angle with respect to the omega. So magnitude ratio is taken as radius and phase angle is taken as theta. And this is a procedure, once again general procedure: step 1, step 2, step 3, step 4. The very first step, carefully note down the transfer function for which you have to prepare the polar plot and identify the type number and order number. In step 2, once again adjust into 1 plus st form wherever necessary, otherwise if it is directly given no need to adjust, and convert the polynomial of s, maybe s to the power 2, s to the power 3, into separate s into s if it is s square, if it is s cube, s into s into s, that is easily convert to 1 plus st form, and replace all the s terms by j omega. So where j is imaginary term, that is I sometime taken as, or j sometime, that is equal to square root of -1, and obtain the equation for magnitude ratio as well as phase angle by using this relationship that is described in step number 4. In step number 5, put the limiting values of omega as 0 and infinity and find the endpoints of that particular polar plot. If it is necessary to find the third point, that is wherever possible to understand the shape of the graph correctly, so that also you have to find out. That will tell the nature of your polar plot. So by that you can find out the wherever the polar plot is crossing the crossover imaginary axis, that you have to find out and find the value of m omega and phi omega for a selected values of omega in the vicinity of crossover and tabulate the values. So by taking suitable scale, locate the points on the polar coordinate and draw the smooth curve passing through all these points, and show the angles in the clockwise direction, that is negative angles: 0, -90, -180, -270 and -360 and so on, and to obtain the the polar plot. So with this I can conclude my session 1. Thank you.